In this video, we're going to do some calculus on functions that are defined in polar coordinates. So, in particular, we're going to be interested in doing area problems in polar coordinates. So, let's say we have a polar function, r equals f of theta, and we want to do the area between the function and the pole from one angle to another. So, just to show you what we're talking about here, here's the graph r equals f of theta. Here's the pole. So again, when we're tracing out the function, remember we think about rotating from the positive x-axis, from the polar axis here. So really what we're doing here is we're sweeping out an area rather than making it more of a rectangular region. Okay, so this is the region that we're talking about here. But we're going to attack it in the same way that we attack problems in rectangular coordinates. We're going to slice up our region into pieces that we know what the areas are, and use those areas of those small pieces to approximate the bigger area by adding up all the areas of the small pieces. Alright, so we're going to do that in this case. We're going to divide the interval from a to b into n subintervals of equal width. What we're going to do here, though, is we're going to use pie slices, if you will, or sectors of a circle, to approximate the areas. So right here we've got a representative pie slice. So this is a little arc of a circle, okay? So we're looking at this little sector. We know that the area of a sector is 1/2 r squared theta, where r is the radius of the sector and theta is the central angle. Well, in this case, the radius is this dashed line that's going up to the function. So what we're doing here is we're going to pick a sample point and use the function to give us an approximation of the radius of the sector. Much like what we did when we took for rectangles, we took a point in the subinterval and used the function to give us the height of the rectangle. And then the central angle that we have here is going to be the little change in angles. We go from theta sub I minus 1 to theta sub I, or call it delta theta. So just to write that down, theta sub I star will be any sample point. We'll plug that sample point into the function. That gives us a radius of the sector. And then the delta angle will be the central angle of that sector. Then we can figure out the area of one of those pie slices to be 1/2 the radius squared times delta theta. Add those all up to get a Riemann sum. Take the limit as n goes to infinity to get a definite integral. And this really should just be f of theta. I don't need the theta sub I star here at this point. Alright, so let's see if we can put that formula to use. So let's find the area of one loop of r equals 4 cosine of 3 theta. So let's start with a graph. I would suggest probably just using your graphing calculator to get a graph of this curve. So notice in this case we get 3 loops. We're just interested in finding the area of one. They all should have the same area in them. Alright. So if we want to find out the area for one of these loops, I need to make sure that I figure out the thetas where this is drawn just one time, right? I need to figure out where this curve comes back and crosses itself at the pole, at the origin. So let's set the r equal to 0. That's when that happens. Go through the inside here. If cosine has to be 0, the inside has to be pi over 2 plus n pi. Divide both sides by 3. Give us pi over 6 plus multiples of pi over 3. Pi over 6 is this one, this angle here, right, coming in this way. If we think about coming from below, though, and around and tracing this out, if this is theta, pi over 6, so n is 0, we would have to use the n equals -1 to get this angle, or negative pi over 6. So plugging into the formula then, our endpoints are negative pi over 6 to pi over 6, 1/2 r squared theta d theta, or r theta squared d theta. Simplify, pull the constant out, use our power reducing formula, find an antiderivative, plug in the endpoints, and get 4 pi over 3 in this case. Again, like I mentioned, it's very important that you've got your angles correct here for drawing this out exactly one time. You don't want to say 5 pi over 6 to pi, or excuse me, 11 pi over 6 to pi over 6 doesn't make any sense. You also don't want to do pi over 6 to 11 pi over 6 because that would go this way. We would find the area of those two loops. Okay. So it's kind of the one thing that you have to be careful of, is making sure that you're only drawing out the curve one time and making sure the interval makes sense for how you want to draw out that curve. All right, let's do another one. Area inside r equals 1 minus sine theta and outside r equals 1. Again, start with a graph here. Here's r equals 1. That's a pretty easy graph. R equals 1 minus sine theta is this graph. This is what we refer to as a cardioid. Inside the cardioid, outside the circle. That's this piece down here, right? These pieces down here. Okay. So we want this area. So to get this area, notice if I think about shooting rays out from the origin, out from the pole, through the region, thinking about like almost a second hand sweeping this out. Notice it comes out, it hits the r equals 1 curve and then hits the r equals 1 minus sine theta curve. That tells us we're going to have to subtract a couple of integrals to figure out the area. All right. So I need to go from this point here all around this way to this point here. So it's hopefully it's pretty clear that we're going to use pi and something over here, 0 or 2 pi, right? Probably 2 pi since we have to go from here and around this way. But let's just set things equal and make sure that we really do get that. So set the 1 minus sine theta equal to 1, get sine theta equals 0, and that really does happen at the multiples of pi. Now again, we want this part down here, right? We start here and keep rotating around this way. So we don't want to say it's 0 to pi, that's up here. We want pi to 2 pi, that's what's down here. Okay. So from pi to 2 pi, the r 1 minus sine theta is farther away from the pole than the r equals 1. That tells us that we're going to do the subtraction of those two integrals. So let's set it up. From pi to 2 pi, 1/2 times 1 minus sine quantity squared d theta. That would give you, if you were just thinking about what this area represents, it's here, around here. So it's all of this area, all of this, including what's in the circle here, below the x-axis. So we subtract off the 1/2 times 1 squared d theta. That's this area of the circle here. Or think of it as an area of that semicircle. You can just subtract that off. So the second piece here just becomes pi over 2. Over here we'll FOIL and use our power reducing formula and simplify. Find an antiderivative. Plug in your endpoints. So in this case, we get the area as 2 plus pi over 4. Again, the reason why we subtracted here is because as we come out from the pole, we don't want this area included in here, right? Remember that integral formula that we came up with was from area between pole and curve. We don't want this area, so we need to subtract it out. Let's look at another example. Let's find the area inside both r equals 1 plus cosine theta and r equals 1 minus cosine theta. Just like we started the previous two problems, let's get a graph going to start with. So this one is your r equals 1 plus cosine theta. Here is your r equals 1 minus cosine theta. All right, so the area that we're interested in here is these two little pieces in the middle. So in this case, our plan of attack actually will be to find out the area of one of them, and then we can use some symmetry and double it. So really, let's just look at this piece. All right, so this is your r equals 1 minus cosine curve. Notice again, if we go out from the pole to the graph, notice in this case, when we're in the region, we're entirely in the region as we go all the way to there. Once we get to pi over 2, the bounding curve changes, but we still only go from pole to curve. We don't need to subtract anything here now. What we need to do is we need to integrate one of them to find basically this half of this area, and then integrate the other to find this other half, or it's split in two. All right, so again, this is what I just said. From 0 to pi over 2, 1 minus cosine theta bounds the curve. From pi over 2 to pi, 1 plus cosine theta bounds the curve. So we'll add two integrals together to get the area of one of them, and then we'll double to get the total area. So double the integral from 0 to pi over 2 of 1/2 1 minus cosine theta squared, and then plus pi over 2 to pi integral 1/2 times 1 plus 1 cosine theta squared. Foil it out. Foil each of them out, I should say. Use your half angle formulas or power reducing formulas, whichever you want to call them. Find your antiderivatives, plug in your endpoints, and simplify, and get to an answer of 3 pi over 2 minus 4. So the moral of the story here is it's important to make sure, am I subtracting two integrals because I have two different bounding curves, kind of a top and a bottom? Really, it's a farther away and a closer. Or does it switch bounding curves in the middle, like this example did?